Okay, now we can start with the relatively dedicated concept of sampling of two-dimensional signals. We have seen all the sampling recitation. We have recited all those things just to make sure that we are comfortable with the information that we will deliver, particularly for two-dimensional or multiple dimensional signals. So, 2D sampling is our topic right now. Now I will draw an axis so that we remember the fact that periodic sampling requires periodicity, and the concept of period in two dimensions require two vectors or forming a matrix. So we have four numerical values to represent a periodicity, and we will therefore first define a lattice. Let me show you the lattice. I say that these red dots and these red dots, they are corresponding to a vector like this, and then we have other things like okay, right in between them. Clearly, these green dots and the red dots do not mean different things. All these samples that I'm showing here are essentially the sampling points, the sampling grid, regardless whether it is green or red. It doesn't really matter. I don't want to separate them. I just want to, I just put them in different colors to make sure that the concept of, let's say, V1 and the green V2 makes sense, because with respect to a periodicity, these are the periods that we have, and as you see, it's like a rectangular sampling matrix, but rotated 45 degrees. Okay, that's also possible. I mean, in image processing, any kind of sampling is possible. You may just hold your camera, for example, a square grid sampler, CCD sensor, 45 degrees tilted, and you may take a picture of it. Then that would really correspond to this kind of a sampling situation. And every point would physically correspond to an expression like N1 times V1 vector plus N2 times V2 vector. Normally, in one-dimensional signals, we had N times T, capital T, which is corresponding to every point on the one-dimensional function. But now we don't have N times capital T. We have, first of all, two points or two scales, two integer scales that multiply the period, and we have two periodic vectors. Two vectors must be defined. And this expression can be put into something like this. V11 and 1. Let me write it. V12 and 1 plus V21 n2 plus v2 2 n2, which in turn can be written as a V matrix consisting of V1 and V2. So let me show this as V1 and V2. Okay, I form a matrix times an N vector consisting of N1 and N2. So if you remember, in the one-dimensional case, we were having like N times capital T. Now it's converted into, or capital T times N, you can think of it like that, as capital V times N. Capital V here is the period matrix. And since it's in the form of a matrix, it is multiplied only with a vector to come up with all the points on the grid, any point along this grid that I wanted to indicate. All right, so we can make an analogy like T is converted to V, and therefore, or V matrix, of course, X of T sampled by capital T will be converted to, so this is a double arrow, X of T vector is sampled by, let's say, the V matrix. So these are the notations that we are going to use. And the sample points will be at the T vector, which is, of course, T1 and T2. Let's be clear about this. Whenever that T is equal to capital V times N, whenever we hit the location of the period at the point of the repetition, whenever that is the place, we sample at this point. So we sample at these points. Of course, for all integer n. For all n, an element of n square. It's a vector with two integer elements. So these are our sampling points. Now the special case happens when V1 vector is orthogonal to V2 vector, and we call this an orthogonal sampling. And it's quite obvious. A good example for an orthogonal sampling, which is almost always used in the digital cameras for image acquisition systems, it is V1 is equal to T1 0 and V2 is equal to 0 T2. And even better than this, capital T1 is equal to capital T2, which makes a square grid, not even a rectangular one. But we may have other types of samplings, and those samplings we will soon see when we see the repetitions of those. You remember the repetitions of the triangles at 2 pi when you make sampling in one-dimensional signals? So those triangular waveform, the Fourier transforms, they mustn't touch to one another, right? So we must have a large separation. Let's think of the two-dimensional case of a Fourier transform. It's easiest to think of a continuous time surface, the Fourier transform of a continuous time surface, like capital X of, let's say, omega bar, where this is omega 1, this is omega 2 axis. Let's also assume that it is band limited. If it is not band limited, we have to apply a low pass filter to avoid aliasing. But it may be, I don't know, let's think of it as a circularly symmetric shape, a band limited shape. And inside this one, it contains values. Out of it, we have nothing. So it is indeed band limited. When we try to find the minimum T1 and T2, when we try to minimize these, it would be like 2 pi over capital T1 would correspond to a high frequency. Or excuse me, we are not trying to minimize. I will have to erase this. We are trying to minimize the sampling frequency. So that corresponds to a maximization of T1 and T2. So I want to really sample as sparse as possible. And why is that? Of course, as long as I don't lose any information, then it means that the amount of data I want to carry or store would be minimized, because the number of samples would be less for larger T1 and T2. But then that means 2 pi over capital T1 and T1 and 2 pi over capital T2 are minimized or are minimal. When they are minimal, of course, we have to take into account that we don't want aliasing. So I want to merely touch the shapes of those triangles or these circular shapes, disc shapes that I indicate. Where will they be? What is the minimum choice of T1, sorry, maximum choice of T1 and T2, or the minimum choice of omega S1 and omega S2? What are the minimal choices of those? I think you will understand when I draw it that the minimal choice of omega S1 is somewhere here, so that when I make a replica, where do these replicas come from? They come from convolution with impulses, because again, we are multiplying with an impulse train, and the impulse train in time domain is not a train, but it's like a bed of nails. So let me try to indicate the time domain sampling. The time domain sampling would be like this. So every point that I draw here, this is T2, this is 2T2. So every point that I draw here is like a nail protruding towards me. All right. So if you want to visualize it in 3 dimensions, the situation is like I have an impulse here, another impulse here, here, and here, 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 etc. They are towards the surface. So it's more like a bed of nails. Okay, some strange shape. So those bed of nails are actually they are pressed on a surface, and by pressing on a surface, you pick the samples of those values, and those values will make these nails to have different lengths, different magnitudes. That is the shape of which I'm taking the 2-dimensional Fourier transform. So I apply it, and then I take the Fourier transform, and I get this picture. Okay, that's what it really corresponds to. And since I'm multiplying with the bed of nails in the time domain, I have to be convolving this disk shape of the Fourier transform with the Fourier transform of the bed of nails. So what is the Fourier transform of bed of nails? It is another bed of nails. That's because the impulse train's Fourier transform was another impulse train. Only the separations were different. If the impulse train was separated with capital T, then its Fourier transform impulse train samples were separated by 2 pi over capital T. That's why the separation of the bed of nails of the Fourier transform is omega S1, which is 2 pi over capital T1. And of course, we have all other replicas too. This is omega, twice omega S1. And vertically, this must be omega S2 and therefore we have these replicas to the top, to the bottom, everywhere. So we have this kind of a situation. This is, by the way, the convolution of this central disk with an impulse train. I'm just drawing the result here, like this. Of course, maybe I should be indicating or giving some names to these signals. This bed of nails, for example, that are separated by T1 horizontally and T2 vertically, we can give a name to that. Was I using a name for this one? I don't know, maybe P of T. Let's P of N. No, P of T, excuse me. P of T vector. This is the bed of nails. That P is a lowercase p, by the way. And the Fourier transform of this P of T is capital P of omega. When we plot it, let's plot it on green. Let's use a different color. They will be separated horizontally by omega S1, 2 omega S1, 3 omega S1, and vertically again by omega S2, 2 omega S2, etc. So it's going to be these points, of course, infinitely extending like this to the left and to the right. Where omega S1 is equal to 2 pi over capital T1 and omega S2 is equal to 2 pi over capital T2. So when I convolve these two shapes, when I convolve the black one, excuse me, I have to convolve it with this one, with this black disk. When I convolve these points with that black disk, I will come up with this result. Now, the thing is, regarding the pixel density here, we are trying to maximize the pixel density, or in other words, minimize the number of pixels to represent this image. When you stack those disks like this, so that they don't touch one another. The problem is, or the question is, let me move to here and ask this question. Is this shape good? Or is the pixel density highest? Or is the number of pixels for representation minimal? They correspond to the same question all the way. And the answer, when we visualize this stacked disk shapes, is that it's not. We will define the pixel density very soon. It's actually corresponding to the determinant. Pixel density is related to the inverse of the determinant, the absolute determinant of V. What is V? What was V? It was equal to T1 0 and 0 T2, right? So the determinant is equal to T1 times T2. Now, can we get something smaller than this one? Let's focus back to this shape. I'm sure most of you guys have been playing with marbles at home or on the streets, okay? The small marbles where we kick one another's marbles all the time to grab or capture the opponent's marbles. But one thing that you may have noticed is that this is not the most compact way of putting all the marbles on the surface, right? They tend not to sit in this kind of a layout. When you try to compress them, when you try to squeeze them on the surface, let's say on a carpet or something, they tend to be getting more compact than this one. And that is always found in the nature as well. For example, the honeycombs of the bees, honeybees, are never like these square boxes. They never do it that way. The square boxes do not appear in the nature, but hexagonal boxes appear in the nature. So when you try to improve the efficiency of these marbles or of these discs, what you come up with will be more like this. We have a circle here, and we want the replicas of these circles to be, but I don't know how to really, maybe it must be here or something. I don't know. But because this is a square grid that I'm plotting on, and square root of 3 is, I cannot locate where square root of 3 is here, but it's gonna look like, I see, now I get the picture. It must touch somewhere here, and the situation will be like this. It's a little bit more difficult to draw, unfortunately, as you see. But you get the picture. This thing is more dense in the, or more compact in the frequency domain, because this is omega-1, omega-2 domain, right? If you may remember. So this is the natural way of squeezing things as much as possible. And if this in time domain corresponds to a sampling, then the number of samples will be minimal, and the sample density will be the maximal. It is the most compact way of representing this circular Fourier transform, or the shape with that circular Fourier transform, with as few pixels as possible, or with as separated sampling periods as possible. I'm trying to separate the sampling periods. Now, I couldn't do that in the previous one because they were touching. I cannot choose a smaller T1. I cannot choose a larger T1 and make it wider sampling for less number of samples, because when I increase T1, it decreases omega S1 and they start overlapping. But this one corresponds to some other situation. We will define the situation in the Fourier domain, not in the time domain, like this. This will be, let me use black, omega S1 vector, or omega 1, you can also say. And the other one, maybe this one, you may choose omega S2 vector. So I have two repetition periods in the 2 dimensions. And I'm going to denote it or give a name to that. But what is the name that I'm going to give? Because I haven't done that in my notes. But let me give a name. Let's say that it's W. This W matrix is the periodicity matrix in the Fourier domain, consisting of omega S1 vector and omega S2 vector. What kind of a sampling matrix, or what sampling vectors does it correspond to in the original time domain, in the V domain, in other words? Well, they are related to one another with this equation. It's like saying omega is equal to 2 pi over capital T. Okay, from this I come up with this one, 2 pi times, I cannot say over T in the form of a matrix. So for the matrices, I use matrix inversion. Or I could say that V is also 2 pi times W inverse. It's not omega, of course. I'm using an uppercase, like a uppercase W. So this is the period matrix in frequency domain, and this V is the period matrix in space. I should use not time, of course, in space domain. And they are inversely proportional to one another. If you're trying to increase the determinant of one of them, it means you're decreasing the determinant of the other one. Their determinants, their magnitudes, sizes are inversely related to one another. I think it's easiest to find the W for V is equal to T1, 0, 0, T2. Okay, and that would be W is equal to 2 pi over T1, 0, and 0, 2 pi over T2. And as you see, the first row would correspond to omega S1 vector, and the second one would correspond to omega S2 vector. And that's exactly what we got in this example. Okay, in this example, horizontally, it was omega S1 and 0. So this was our first periodicity vector. And the other periodicity vector was 0 and omega S2, this one. Okay, these two could also be confirmed from these formulas between the sampling period in space and the periodicity of the shape in the Fourier domain. They are inversely related to one another within a factor of 2 pi, of course. So, with this information in our minds, now how can we, maybe I should open it in a new page because we are really running out of space. Sorry. So the aim that we have is to find the Fourier relation between the analog or continuous, let's say x sub a of T1 and T2, which could also be written as xa of T vector with an underscore. You can also write it like that. And from there, we sample it to obtain x of n1 and n2. Okay, so what are the relations between the Fourier transform of this one, which I'm going to call as xa of capital omega? I have to switch to the notation of capital omega and lowercase omega to distinguish between the Fourier parameters of continuous time signals and discrete time signals, where the second one will have the Fourier transform of x of, let's say, e to the j omega. Notice that I'm putting bars below, beneath the omegas. It means omega 1 and omega 2 in the form of a vector. So we are going to find, we aim to find the relation between these two. We found it for one-dimensional signals. We already know it. So we will use that much information to literally extend. First of all, we know that x of n is equal to x sub a of sampling matrix times n. Okay, that's how we pick the samples. So, and we also have this information, x sub a of omega, or maybe I should initially write it in the form of omega 1 and omega 2 to avoid ambiguity, is equal to two integrals. Why two integrals? Because it's two-dimensional. So it's a two-dimensional Fourier transform of xa of t1, t2, e to the minus j omega 1 t1 plus omega 2 t2 dt1 dt2, like this. Now please notice that this may be written in a very compact form like a single integral, but that single integration corresponds to a volumetric or two-dimensional integration. Xa of T bar. So this is the notation that we must adapt into. So you should better try to understand how I'm writing the things. E to the minus j omega transpose. So omega vector is transposed to become a row vector. If not transposed, all the vectors are column vectors, okay, vertical. So I make it a row vector and multiply it with a column vector. Excuse me, it's not T1, it's T bar, like this. And I'm writing it like the dt vector. So it's a vector wise integration, but they correspond to the same thing. So the below thing is just a notation to put the expression at its at the above of it in a more compact way. Okay, so from here I can say that xa of t is therefore the inverse Fourier transform of xa of omega. Okay, and that would be, it's like showing your left ear with the right hand like this, but when the formulation is inserted into the correct place, this would be meaningful. First, I'm writing the signal in terms of its inverse Fourier transform of the Fourier transform, and that also gives you the notation of how to write the inverse Fourier transform, by the way. That is xa of omega e to the j omega transpose t, and this is d omega. So these two things are actually the Fourier transform formula for two-dimensional signals, continuous time signals, in other words. So when I write it like this, I can now substitute t is equal to v times n, which corresponds to the sample points. Now, at the sample points, what happens? When I write it like this, the left-hand side of the equation becomes xa of v times n, which is actually x of n in discrete time, is equal to 1 over 4 pi squared. Now I will substitute to the right-hand side of the equation xa of omega e to the j omega transpose times v times n, because t is equal to v times n, d omega. Okay, now I will make another substitution. The substitution is as follows. I will call this capital omega transpose times v to be equal to lowercase omega. So I will substitute omega is equal to, but it's not omega, it's let's say omega transpose, I'm sorry, because that would make a little bit more sense. Okay, omega transpose is equal to capital omega transpose times v. Okay, with this substitution, I will have some problems with this one, because of course omega is therefore related to must be converted, and the case omega is equal to 1 over determinant of v. This comes from the so-called Jacobian, you may remember from calculus, or if you have seen vector calculus, the omega. So every time I see omega, originally I should put lowercase omega times V inverse or something like that. But if V inverse for the D uppercase omega reflects in the form of 1 over determinant of V, because these are, it imposes a scale in magnitude as well as in the vector domain. So I have to make these two substitutions. So I have to replace every omega transpose, or every omega, as omega transpose is equal to lowercase omega transpose times V inverse. And when you take the transpose of the both sides, their orders are interchanged, and omega becomes V inverse transpose times omega. So I will substitute omega with this one, the last thing that I wrote, and d omega will be 1 over determinant times d omega. These are the substitutions that I will make to come up with the final expression, which gives me x of n is equal to 1 over 4 pi squared integral. This 1 over determinant of v, that is in d omega, I can write it, let's say here, 1 over determinant of v and x a. Instead of omega, I'm going to write v minus transpose, v inverse transpose lowercase omega, and this will become e to the j omega transpose and d omega. So this is the it's like the inverse Fourier transform of x of n, but it's not really the inverse Fourier transform, because the inverse, in the inverse Fourier transform expression, in the original inverse discrete time Fourier transform expression, it should be like this. I'm writing in red. X of n should actually be 1 over 4 pi square from minus pi to pi, or within a duration of 2 pi. If you may remember, in discrete time, the inverse Fourier transform must have contain an integral with a duration of 2 pi. And the Fourier transform, the discrete time Fourier transform, which was like this, okay? And e to the j omega transpose. These are, by the way, vectors. I forgot to mention them. So let's make everything as a vector. Omega transpose and d omega. Okay. So these two equations both correspond to x of n, and it gives us a relation between the Fourier transform definitions. Then how can we relate this? To this? They should be more or less the same thing. I'm saying more or less because their integration limits are different. One of them is an integral from minus infinity to infinity. The other one is from minus pi to pi. So how do we relate these two things? We must make this kind of a remembrance. So I'm drawing it in blue. I will say remember the following. If you are trying to take the infinite integral of f of t dt, where this is periodic, if f of t inside it is periodic, you can do it like this. You can take the integral within a period and then sum up for all periodic replicas of this within one period. Okay, you can relate a periodic signal to one portion. I will put F1 here, which actually corresponds to one period of f of t, okay, in this kind of a format. And writing or being able to write it like this will help us to relate these two in this way. We will write now x of n. I'm taking the first equation, not as an infinite summation. With a 1 over 4 pi, it's 4 pi square, it's still there. But I will write the integral as in one period from, let's say, from minus pi to pi. And 1 over absolute determinant of v times summation over k. I'm applying the blue line here. xa v inverse transpose. Now, for omega, lowercase omega, it has to be periodically repeated like this portion here. So I'm writing omega minus 2 pi k to make 2 pi replicas, both for omega 1 horizontally and omega 2 horizontally. It's a periodic replication, of course, in 2 dimensions, because the integral symbol itself is not one-dimensional integral, it's a 2-dimensional integral. I'm just writing it as if it is, there's a one-dimensional integral, but it's just a notation. And the same also applies to the omega at the exponential, e to the j. Instead of omega, I will write omega transpose minus 2 pi k transpose. I could put the transposition after the parentheses times n, and finally d omega. Now here, this time, by making this kind of a substitution, it a little bit looks like this red formula, because at least the integration is from minus pi to pi. But the exponential term looks a bit awkward, because here I don't have e to the j omega transpose n. I have e to the j omega transpose minus 2 pi k for some number, integer numbers of k times n. But it's equal to e to the j omega transpose n times e to the minus j 2 pi k transpose n. Okay, this exponential. And this point is always e to the minus j, or times 2 pi times an integer, because k transpose n is integer. K is consisting of integer elements, n is also consisting of integer elements. When you multiply the first row vector with the other column vector containing all integers, it will result in an integer number. So this part is integer. Therefore, e to the minus j 2 pi times an integer is what we get, which is 1 always. Okay, so the exponential term, although it looks like e to the j omega transpose minus 2 pi k transpose times n, actually it is e to the j omega transpose n only. We will only, we will only keep this portion and write it that way. In fact, I will write it now. That is equal to 1 over 4 pi square integral within a 2 pi period and 1 over determinant of V, this summation over K XA of, not, why am I writing E? XA of V inverse transpose. I'm just repeating what I have over there. Omega minus 2 pi K times e to the j omega transpose n d omega. So this is eventually what we get. And now we can safely say that this thing that we have here is the same as this that we have. They correspond to the same equation. So let's equate them. That's the last thing, almost the last thing that I will write, because we have to be careful about where K is ranging from and up to. It's not an infinite summation now, because we have infinite replicas within the period. So K is not from minus infinity to infinity. It is something, and we will associate it with the one-dimensional case very soon. This is equal to, no, it's not, I'm not saying it. I'm saying x of e to the j omega is equal to 1 over determinant of v times k xa, let me repeat, v inverse transpose omega minus 2 pi k. Okay, that's what we have. Now this expression resembles the sampling. Oh, excuse me, this K is, by the way, from minus infinity to infinity. I was saying it's not from minus infinity to infinity. I was confused with the downsampling issue, but this is not downsampling, this is sampling. We are doing sampling right now. So K is indeed from minus infinity to infinity. If you remember, in 1D, the formula was 1 over capital T summation x continuous or analog, whatever, times omega minus 2 pi k over capital T. Right? You may check your notes and see that the one-dimensional sampling formula was this one, and now we have this, and it seems legit, right? Legitimate, because they correspond to exactly the same things. The magnitude of T corresponds to the determinant of V, absolute determinant, and voila, this is what we have. But I was maybe using one awkward terminology by saying that the summation, maybe I should correct it here. The summation K here, which is an infinite summation, is actually a two-dimensional summation. So I'm putting bars under K's every time I see, even for the summation run. So I cannot really write it like from minus infinity to infinity, but it is K1 from minus infinity to infinity and K2 from minus infinity to infinity. So let's put this thing in a box, because that will tell me how to make 2 pi periodic replicas. For instance, suppose that we have, this was a bad one, sorry. Suppose that we have the Fourier transform, which is xa of omega over the omega 1 and omega 2 axis, like this. When we make replicas of these, it will produce replicas with respect to 2 pi over, or 2 pi times V inverse. The first example that we did was V is equal to T1 0 and 0 T2. So that corresponds to the simple rectangular sampling, T1 0, 0 T2. So that makes W to be equal to 2 pi over T1 0 and 0 2 pi over T2. This is the simplest sampling. Now assume that your shape here is like this. It's not a disc this time, but it's just a diamond shape like this, or 45 degrees rotated square shape, which is indeed a diamond shape. And these 2 pi over capital T1s will now be the positions where we repeat these diamond shapes. So after sampling, but it's not sampling, but it's like multiplication with a bed of nails. I didn't come up with the discrete time image yet, not the digital image, but I'm just repeating. These diamonds will be repeated according to whatever omega S1, which is 2 pi over T1, and omega S2 corresponds to. This is 2 pi over T1, by the way. And let's say that uh, 2 pi over T2 is here. So we have this kind of repetitions, horizontal and vertical. Obviously, horizontally, the separation is a little bit larger, which means T1 is smaller than T2, because vertically, they are a little bit closer to one another from the shape. I mean, just in this example. Like this. Right. On the omega 1, capital omega 1 and omega 2 axis. And multiplication with a bed of nails gives you another bed of nails, but the nail sizes are different. It depends on the surface profile or the continuous time image. So this is the thing that you have as an intermediate step. And from this intermediate step, you have to convert to 2 pi periodicity. And then you will get a little bit distorted version of this black shape. Maybe I should draw it with blue. If you convert this one to omega 1 and this one to omega 2, so I'm drawing x of e to the j omega. Now, this last thing that I will draw, the blue shape, it will look like the black shape above it, but it's not going to be periodic with 2 pi over T1 horizontally and 2 pi over T2 vertically, but it will be periodic with 2 pi at both directions. So this new period will be 2 pi, both horizontally and vertically. This will be 4 pi, and this will be 2 pi, the same 2 pi in size, etc. Minus 2 pi, minus 2 pi. And these diamond shapes will be repeating at these 2 pi ranges, including here and here and here and here and here. But we have to be careful about one puzzling situation. The situation of the puzzle is, as you see, conversion of 2 pi over capital T1 to 2 pi and 2 pi over T2 to 2 pi are not the same. So horizontally and vertically, these diamond shapes will be not scaled at the same proportion. It will be most probably the diamonds will be narrower horizontally when you make this kind of a sampling. Sorry for my bad drawing. Something like this. But nevertheless, the last thing that we draw, the blue shape, which is the Fourier transform of the discrete time signal, this one, in other words, is 2 pi by 2 pi periodic. This must be 2 pi by 2 pi periodic. If you, in an exam question or in an answer to any kind of question, if you give me a two-dimensional discrete time Fourier transform of a two-dimensional discrete time signal, like an image, and give me a result which is not 2 pi by 2 pi periodic, it means you are making a mistake. It cannot be. It must be 2 pi by 2 pi periodic. And this example that we did is essentially the easiest example that you can ever imagine, because this V is easy. It's the easiest V. But do you remember how we were doing the hexagonal sampling, for instance? We have to see further examples, probably next week, to sample the continuous time surface with hexagonal sampling. And with hexagonal sampling, the repetitions, let me close this page and go to the previous one. Yeah, here, these repetitions, they are on the uppercase omega axis. They are in the continuous frequency, the continuous time Fourier transform axis. So when we convert these hexagonally stacked discs, these shapes, these marbles, or the other diamond shape, when we hexagonally stack it like this, they will be very much stacked. But when you convert it to discrete time Fourier transform, you have to make them 2 pi periodic, 2 pi by 2 pi periodic. Where, as you see, these hexagonal samples are not 2 pi by 2 pi periodic in their original format. You must make a smearing, some rotation and scaling at the same time, which is a smearing effect. So smearing wise, these must be corrected to become 2 pi by 2 pi periodic in the Fourier domain. So the results will not be like these circles anymore. When you look at the discrete time Fourier transform, they won't be circles. When you look at the bed of nails Fourier transform, it will be circles, but it will not be 2 pi periodic. When you convert it to 2 pi periodic, it will not be circles. It will be probably ellipses. And the others, these, they will not be, when you do, of course, hexagonal sampling, they won't be diamonds anymore. When you do normal rectangular sampling in the Fourier domain of the discrete time, they will still look like diamonds, like this. But if the sampling that we use will not be rectangular, it may be just any sampling matrix, as long as it's non-singular, any matrix will do with that sampling matrix, after bed of nails, they will look like diamonds located here and there, periodically tiling in a form of a lattice. But when you transform it to become 2 pi by 2 pi periodic, which is the discrete time Fourier transform, they will be rotated, smeared, etc. They will probably be parallelograms or something like that of some sort. God knows what they will be. But we will be doing some examples with these ones because that's critical. And in terms of exam questions in take-homes, clearly I'm going to give you a random sampling matrix, and I will like you to draw the shapes of x of e to the j omega. We will have to do that. So we will see some examples, but the examples that you will encounter or the questions that you will encounter in the exam may be a little bit tougher than that. Yet you will have, for the take-home examination, you will have a lot of time to solve those things. All you have to do is you have to be careful. We haven't finished yet. We will do that. We will see a hexagonal example. But in the exam, you will not encounter a hexagonal example either. It will neither be rectangular nor hexagonal. It will just be an arbitrary sampling matrix. And let us see how you will perform for sampling that one. And so why are we doing it? Well, as I said, we are doing this because it may be more efficient. The sampling density is an important concept, and we want to make these Fourier shapes as close to one another with minimum amount of empty space as possible. And unfortunately, rectangular sampling will not help us do that. So next week, we will continue from there. Now, I can ask whether you have any questions or not. If this is a little bit heavy, on the heavy side, you may want to review what we have done. I'll try to put these on YouTube, these videos, so you may want to watch them again. But nevertheless, if you have any questions. Okay, Işıl, you have a question.
Hocam ben bir şey soracaktım ama gelen mailde mühendislik fakültesinde birinci sınav haftasının 16-20 Kasım olduğu yazıyor ama.
Okay. Mm-hmm. Then it is. Then I will submit the take-home examination towards that date. Maybe ama, it's not the...
Yine de şey olacak mı? Biz bu bahsettiğiniz konulardan sorumlu olmayacağız mı?
What do you mean?
Shape olarak haftaya yapacağımız konulardan.
Yes, you will be responsible from the things that you will see next week.
Okay.
I will submit the examination after the first midterm by the end of next week, Tuesday. Evening Tuesday. So we will first do some lecture and then I will submit the examination. And you will have 1 week. Okay? So maybe I was kicked away from it went into a sleep and so there was a problem. But nevertheless, we have finished the course anyway. So any other questions? So you will be responsible for the content that we will see next week. That's certainly. No matter whether the exam week is next week or the week after that. Whatever we will see next week, you will be responsible in the midterm. Okay, any other questions? All right, no further questions I see. So I stop the recording and we will meet next week. We will do the class. And by the evening of next week today, I will be submitting a homework on the Canvas system. I don't know where I will put that one. It will not be in the exam section because it's for doing other types of examinations, not take home. Maybe, I don't know. Just beware, okay? Watch where I'm going. It may be in the announcements. It may be in another module or something like that. We will communicate. Or it may be even a better idea if you just send me your emails by email, of course. And so that I will know your emails and I will send the exam by email. But that's a little bit risky because right now we are not all of the class and I want to send the exam to all of the class. So I will put it on the announcements and in the exam section or something like that. We will do it that way. So until next week, take care.